The Big Theorem establishes a hierarchy among the most common families of sequences. It tells us which sequences grow faster than which ones. I assume you have already watched the previous video, where I introduced the theorem, I explained the notation, and I showed how to use it. There is a link in the description. In this video I will present a proof. As a reminder, the Big Theorem says that logarithms are much smaller than powers, which are much smaller than exponentials, which is much smaller than factorials, which is much smaller than power exponentials. This is actually 4 different claims. In order to prove the theorem, I will need to prove all 4 claims. For example, I need to prove that the limit as n approaches infinity of a logarithm over a power is 0, and so on. The first 2 claims are easier to prove. The sequences involved, logarithms, powers, and exponentials, can be extended to functions defined with domain all the positive reals, not only the naturals. Therefore, we can use L'Hopital's rule. I will leave this as an exercise. I invite you to try to write down the proof. It's just a standard use of L'Hopital's rule. The last 2 claims are more interesting. They involve n factorials, which is only defined when n is a natural number. Therefore, we cannot prove them using L'Hopital's rule. We will have to use other tricks. Let's do that. I will begin with the third claim. I want to prove that an exponential is much smaller than a factorial. Let's fix a real number c greater than 1, and let's define Pn to be c to the n over n factorial. I want to prove that the sequence Pn has limit 0. Here is the key observation. If I write the n plus first term of the sequence, p sub n plus 1, it is c to the n plus 1 over n plus 1 factorial. I can factor out a c from the numerator and n plus 1 from the denominator, and I am left with c to the n over n factorial, which is p sub n. So this sequence satisfies the recurrence relation. P sub n plus 1 equals c over n plus 1 times p sub n. And the whole proof is based on this identity. I will proceed in 3 steps. First, notice that the sequence is eventually decreasing. For large values of n, p sub n plus 1 is smaller than p sub n, because p sub n plus 1 is a number less than 1 times p sub n. This is true whenever n is large enough, or greater than or equal to c, so the sequence is indeed eventually decreasing. Second, notice that the sequence is bounded below by 0. And now, since the sequence is eventually decreasing and bounded below, it must also be convergent. This is due to the monotone convergence theorem for sequences. Great. Now that I know the sequence is convergent, let's give a name to the limit. Let's call the limit L. And once we know this limit exists, it is going to be easy to prove it is 0. Let's look back at the recurrence relation. I can use the limit laws and say that the limit of p sub n plus 1 equals the limit of z over n plus 1 times the limit of p sub n. I can only do this because I know all 3 limits exist. The first limit is L, the second limit is 0, and the third limit is L. So L equals 0 times L, and L is 0, which is what I wanted to prove. Great! I want to repeat an important observation. All the steps were necessary. The last part of the argument, proving that L is 0 from the recurrence relation, only works if I already know the sequence has a limit. Otherwise, if I only wrote the last part, I could not be proving that the sequence is convergent to 0, I could only be proving that the sequence is either convergent to 0 or divergent. We have one more claim to prove before finishing the video. I want to prove that a factorial is much smaller than a power exponential, or in other words, that the limit as n approaches infinity of n factorial over n to the n is 0. This will be short. I am going to write n factorial as 1 times 2 times 3 ... times n, and n to the n as the product of n copies of n. Then I group each term in the numerator with one term in the denominator, and now I'm just going to separate the first term. So I have 1 over n times a bunch of factors. Notice that every factor inside the bracket is smaller than 1, and therefore the whole product is less than or equal to 1 over n. concluded that n factorial over n to the n is sandwiched between 0 and 1 over n. Do you see where this is going? We know that the constant sequence 0 and the sequence 1 over n both have limit 0. Therefore, by the squeeze theorem, the sequence sandwiched between them also has limit 0. That is what I wanted. And this completes the proof.